It's my privilege to invite a distinguished academician, researcher, and mentor who has made remarkable contribution in the field of advanced electronics and computing technology. Dr. Sujay Dev sir is an institute chair officer in the Department of Electronics and Communication Engineering and Computer Science Engineering at IIIT Delhi. He earned PhD from Washington State University in 2012. He is a recipient of the DST Inspired Faculty Award and has received multiple recognitions for his research, including Best Paper, Poster Award, and leading international conferences. So now I request Dr. Sujay Dev sir to kindly come forward and deliver this session.
Thank you. Good morning, everyone. So I'm really glad and thank you for the warm welcome. Here on a very timely faculty development program on broadly semiconductors. So I will basically focus on my discussion here. So I keep things interactive, and given that many people are coming from different backgrounds, different of electronics, I'll try to link it with how we all can contribute in the semiconductor mission, which we are very excited. Right? So there is a lot of focus from government as well as different funding opportunities are also available. Okay, so as things get set up, in the meantime, we can try to understand that where maybe we as engineers can contribute take part in this semiconductor mission or design things for us. Now, some of you might think that why we need to design things for us, or why you need to design semiconductor for us. Even if you take aside the requirements of let's say strategy, where if you want to buy a smartphone, so and you want a new feature in that smartphone, if you have which most of us have no how that new feature can be added, or let's say a smartwatch which can monitor my health, that kind of features are not. And the features which are there have been
इसमें तो काला आ रहा है हाँ पूरा काला आ रहा है मतलब लाइक पूरा डार्क ग्रीन
solutions are also
ये तो बाहर से वाली बात है सर
that particular geographical location. There is another big change.
डिस्प्ले
We are already surrounded by electronic gadgets, but we also want gadgets to understand us. We want our, let's say, home automation device to be able to basically play the right music at the right time. So when I go home, maybe in the evening, I want a particular kind of lighting at home. So we want personalization. And this thing will be much more going forward. Let's say 5 years back, we could not stream videos so convenient. Now we don't even think of streaming videos on our mobile phone. 5 years ahead, maybe our fridge will be more intelligent that in a way that it will allow or it will send me alarm about okay, this item is running out, or this is the thing which you need to determine today, so on. So we really don't know what the future looks like. But if we want to control and we want to contribute in that future, we need to design things ourselves. We should not be just be user. Now, where to start designing things ourselves, right? So that's why I would like to focus and possibly motivate all of us to design and building future-ready semiconductor systems. And it's not a not something which is like because if we can do it in software, so nobody questions our capabilities in software, right? So it started maybe in the mid 80s. Okay, everybody and they started writing very smart software systems. Are the leaders in software systems. We had opportunities earlier also in semiconductor domain, but we, for some reason, could not grab that. We have been since then primarily users of uh, the devices which others produce. At some point, we were so focused on, or we were so big users. Uh, if there is a hardware project you need to do, you invariably start or a Raspberry Pi. We generally don't think beyond that. If you need to design a, let's say, line follower robot, you can buy off-the-shelf components, put them together, just assemble things. Without understanding what goes on inside it and how signals are basically sensors are collecting the signals. For example, if a device, if a robot is following a line, what kind of sensors I'm using, how those sensors data are interpreted by the controller, and accordingly the vehicle follows that line. So I think we need to go deeper and we need to understand that because the assembling job is now being done by school students. Raspberry Pi, Arduino, very commonly used by class 7, 8 standard school students. So as engineers, if we are still doing that, then we will be in a bad situation very soon, right? Because we don't need engineers to do that. Now, if we want to go beyond that, if we want to really design things which we can control, we can tweak, we design things from first principle, then we can come up with very unique solutions. And the best part is, or the fundamentals are very, very simple and very much available to all of us. We just need to look into the fundamentals and understand. Don't just treat things as a black box, especially hardware. You should not treat as black box. You should try to know what goes inside. And we can have a simpler view because we are engineers. If things becomes complicated, we will peel off things and basically reach to the level which is simple enough, which I understand completely. Then I build a layer of more understanding. Next version, and so we have been doing it for ages as engineers. So we start with application and we solve that application in physics, but there are a lot of things that goes behind or in between. Now, applications actually tell us that we want, and that needs to be solved using some physics principle. The physics principle we will be is that's the movement of electron, and we can control the movement of electron using the material which is there, for example, semiconductor. We can make some simple setup. Is there a pen which I can use? So the basic semiconductor
This is not working.
We all are familiar with the transistor. So transistor was invented in let's say late 60s. Before that, there was vacuum tubes using which computers are built. So essentially, what we want a switch where we can control the flow of current. Now, in a transistor, like let's say CMOS or NMOS transistor, uh, so we have metal, oxide, and semiconductor. So, so if we draw the basic structure of a transistor, so let's say this is a substrate, there will be regions where we will dope it with N-type material or N-type dopants, and then there will be an oxide layer and a polysilicon or metal layer. Now that's how the name comes, metal. So this is metal or polysilicon. This is oxide. So this is oxide, and then you have semiconductor. So that's why the name MOS, metal oxide semiconductor. Now this we use it as a switch because I can have terminals here calling them drain and source. Now as I apply voltage in the gate terminal, so if it is an NMOS, so I will apply a positive voltage here. So electrons will line up and there will be a channel formed. And if there is a voltage difference between this source and drain, current will flow. Now, if I apply a voltage here, positive voltage, this switch is on. If I remove this voltage, then this switch is off. So this is the basic of a transistor switch. Now, so we are talking about devices. So in this introduction, I thought like I will briefly talk about each of the layers and the key things in each of these layers which we should keep in mind so that we can build system using this kind of abstraction layers. So this is our transistor which we can use for building all our devices. Now, all of us remember the characteristics of a transistor. So if I plot the drain current and the drain to source voltage on the x-axis, and for different levels of gate to so basically our gate voltage, we will see that the transistor ID will vary like this. I'm talking about very basic. Now, when I operate my transistor in this region, let's say I bias my transistor in such a way that I operate in this region and given small input voltage, the transistor will behave like an amplifier. Right? It will amplify the output. So if I change my gate to source, let's say my gate to source voltage, if I change like this, VGS value, if I change like this, the current which will flow through this, the IP will significantly change. So this change will be in millivolt. Maybe this will be at 10x amplified version. So we take the device. If I operate it in this region, I am in the analog domain. We are designing analog circuits. We are designing amplifiers, all sorts of, let's say, your speaker, the mic takes an input and then it gets amplified so that everybody can hear. So this is nothing but you are using your transistor in this region and you are using it as an amplifier. If I use it as a switch, which we are discussing about, either in this region when it is on or in this region when it is off, we are in the digital domain, right? So this is our device. Now using this device, as I was mentioning, we can design different circuits. It could be amplifier, it could be, let's say, some let's say current mirror circuit and so on. Now, using these transistors, we can build gates, which are kind of building blocks for us. Very easy. So basically, let's jump here. So all of us have taken courses in this region. For example, there will be a course on device physics, there will be a course on circuit theory, and let's say this network analysis kind of courses. And then, once we understand all these things, we can move to gates. Now, the simplest of gates is our inverter, right? So inverter is basically, if I give a high input here, I'll get a low output. Similarly, if I give a low input, I'll get a higher input, output, and so on. Now, if you look at what is there inside this inverter, and if we look at a CMOS inverter, so this is how a CMOS inverter looks like. Complementary metal oxide semiconductor. Now, complementary because I have both PMOS and NMOS, and this PMOS and NMOS is connected in such a way that they will not turn on at the same time. If one is on, the other one will be off. So we call it pull-up network, and this is called pull-down network, and we can build family of CMOS circuits using this. Now, of course, we need to be aware of that the inverter characteristics. We expect that if input, so let's say this is input V in and this is V out. So we expect that the if input is low to this inverter, the output will be high. And then after a certain point, if input goes beyond this threshold, the output should be low. So this is what the inverter characteristic should look like. Right? But those of you who have done the experiments, you will see that it never looks like this. It doesn't look like this straight forward, right? So it more looks like this. So at some point, the output starts falling if input increases beyond a limit, and so on. Now, this is governed by which transistor among these two are in which region. So, for example, if your input is really low, let's say I connect to 0 here, then this will be in saturation, the NMOS will be in cutoff, right? Because I'm applying 0, so just here the channel will not form and the NMOS is cut off. So my VDD is, I can imagine that this switch is on, so my output is connected to VDD, right? And eventually when I make this input as high, this NMOS is on, so my output is directly grounded and this is off. So that's how my output will be 0. Now, this looks simpler, but there are many other things. For example, if you want to do this kind of symmetric switching, you need to size your devices appropriately. Now, this in a PMOS transistor, the majority carrier is holes, which has almost half the mobility compared to. Now, what does that mean? It can translate to if both these transistors are of same size, when on, they will have some resistance. The resistance of this NMOS, if both of them are same size, the resistance of this PMOS will be twice compared to the resistance of the NMOS. Okay. So how do we now if I plot this, then it will look like the plot will be my NMOS is stronger, so the plot will move towards this. So I'll not get symmetric switching. As soon as my input goes, let's say 2/3 or 1/3 of VDD, the output will start falling. So if I want symmetric switching, what should I do? I should make the width of this transistor twice compared to this NMOS, so that I have more holes to carry current, and in a way I will make this resistance as R. So both NMOS and PMOS will have same resistance when they are on. So if they have same resistance, then I will get more like the ideal characteristics of an NMOS. And we can extend it to other gates like NAND and NOR, and basically NAND and NOR, as you know, they are called the universal gates, right? So, for example, if I draw a two-input, let's say NAND gate, so it will have, this will be the pull-up network, and this will be the pull-down network. And you can again size them appropriately to get symmetry. So what I'm trying to highlight here is that at each level, there are very interesting things which we can do, and many times we kind of overlook. Now, if I want to build this pull-up and pull-down network having same resistance, the sizing, now I will have this as 2W, 2W, and this also should be, because there are two in series, so each of them has resistance of R. So I want total resistance to be R. So that's why I increase the size of this pull down resistors. So these are primarily field. So again, I can spend the whole time in discussing about these gates, but I want to give some flavor of other instruction, basically levels of abstraction. And the objective of knowing these levels of abstraction is know something of each, everything, basically something of each of these abstraction layers. Otherwise, we will not be able to understand the bottlenecks each of these abstraction layers provide. For example, you might have heard about the latest processor you want to buy is fabricated in, let's say, 7-nanometer technology. Now, what does that mean? To understand that what 7-nanometer means, you need to understand the transistor and the channel length of that transistor. So the 7-nanometer will translate to the channel length of the transistor. So that means my transistor is really now very tiny. And because it is tiny, I can switch it on much faster compared to, let's say, 65-nanometer transistor. Now, whether it needs a 7-nanometer device or not, that will determine what is your objective. For example, you want to open a startup and you want to build some hardware. Now, which technology node you should target? You want to figure out like what is your objective, for what kind of application you are targeting. If the application itself will be running at, let's say, very slow speed in megahertz, then why do you invest in very high frequency transistors, which will are kind of overkill for your purpose? So maybe you can go for 180-nanometer kind of devices. Similarly, whether you would like to use CMOS as your logic family or something like fast transistor. So what is fast transistor? So fast transistor or transmission gate kind of logic also you can use, where so fast transistor is you use one transistor as a switch and using that you build your logic. You can build all your gates, etc. Or you can use something like parallelly connected two transistors, one PMOS and one NMOS, which is called transmission gate, for implementing your logic. Now, anybody can tell why we use transmission gate compared to fast transistor? So this is also a switch, right? So to make this switch on, I have to apply a low voltage, high voltage here, and a low voltage here. So there are one PMOS and NMOS connected in parallel, and I'm trying to use it as a switch. The other alternative is I use one transistor as a switch. So if I apply a high voltage here, it will connect these two terminals. Any reason why I should use this parallel devices compared to this one? This is again a very common interview question, because your NMOS is a good conductor of high voltage. For example, if I have a high here and this switch is on, I'll get a high. No, sorry, I'll get a. It's a good conductor of low. So if I have a 0 here, I'll get a 0 here as it is. But if I have one logic 1, let's say the logic 1 is a voltage level which is, let's say, 3 volt. Okay. So when this switch is on, I will not get 3 volt. I'll get 3 volt minus the threshold voltage of this transistor. So there is a degradation of your signal. Similarly, if it is a PMOS, PMOS can transmit a high value very efficiently. So if 3 volt is your input, you will get 3 volt. But if 0 is your input, you will get a degraded 0. It will not be 0, it will be 0 minus VT. Okay. So that's why this switch will not be an ideal switch. It can only transmit a good 0, not a high. That's why to tackle this problem, you connect this NMOS and PMOS in parallel and make both of them on. So if it is a 0, NMOS, make sure that you get a 0 here. If it is a high, then PMOS make sure that you get the true high. So that's why the transmission gate becomes important. So you can design or you can build gates using this kind of different logic. Now, many job description you might find where it is mentioned that we need RTL design, resistor transfer logic designs. What does that mean? So you use all your basically you after learning all these things, let's say you can design circuits, you can design modules using these different gates, etc. And now you are given a task to design a, let's say, let's say something which is complicated enough. Maybe an adder, not that complicated. Let's say a ripple carry adder. Right? So ripple carry adder, you will have lot of pull adders. So the carry out goes from here to the next carry in. So this is a pull adder, this is a pull adder, and so on. You will get the sum output. Now, these are your inputs. This is your sum output, and so on. Now the carry moves from one pull adder to another, and that's how the sum can be calculated in parallel, but the carry will be calculated only sequentially. So the longest delay offered by this kind of a ripple carry adder will be by the path, basically carry path. Now let's say you want to design and you want to design or you want to use this adder in an ALU, arithmetic and logic unit. Okay. So essentially you have this ALU which needs inputs coming from previous stages, and basically what will be the inputs, etc. Those things will be generated by earlier stages, and you want to sequence those inputs one after another. Let's say you will be doing lot of additions one after another. So what you will do, you want to control how this input comes to this gate, and this control you can do using some kind of a resistor which will be clocked by a clock. So whenever the clock signal comes, whatever is the input to this resistor, that goes to the LED. So this is your resistor. Now, whenever clock comes, you transfer the value from here to here. So that's how this resistor transfer logic works. You might have some other logic here. So you jump from one logic to another logic when clock comes. And again, from here also, maybe you will pass this value through some resistor, which is again governed by clock. So these bunch of these are nothing but bunch of flip-flops called resistors. So you are transferring your logic from one level to another level, and this is why it is called resistor transfer logic. Resistor transfer level. All our complicated sequential designs are done using RTL or resistor transfer logic. Now I would like to go into designing a, or at least give you a glimpse of how a microarchitecture can be designed for a processor. So we look at a very simple microarchitecture of a processor. Now, before I move from this slide, so you see that technological constraints actually give us restrictions that what can be done, what cannot be done efficiently, and so on. That's where the different technology nodes, for example, 3 nanometer, 7 nanometer, they come in. Power dissipation, the battery life, everything is governed by the technological constraints, what you can do at the physics level. Application requirements tell you what you want to do. You want to have an autonomous car. But to implement it, you need a GPU or a bunch of GPU, which will consume a lot of power inside the car. And it has to do real-time processing, etc., which cannot be done if things are very complicated. But that is your requirement. And you can also raise fund. For example, if you want to build a startup, you have to sell the application. You have to tell people what is the problem you are trying to solve and why this problem is interesting to be solved. Because if you can't convince people that what problem to be solved, nobody will fund you. So you get money by selling the application or creating the requirement, but you know the constraints. You know that, oh, I can only, let's say, use a battery which can supply 3.3 volt, not more than that, because it has to and it has to sustain, let's say, full day of operation and so on. So I get application requirements and technological constraints, and these are the abstraction layers, which actually tries to build a bridge between what technological constraints are saying, what application requirements are saying. And these abstraction layers are called architecture. As a system designer, you should be very, very aware of this fact that the solution or the design you want to build needs to take care of the constraint and the requirements and come up with a reasonable solution. There are many examples of how this kind of problems has been solved. One example I quickly mention is nowadays we are very much comfortable using, or all our processors, laptops have multi-core chips, right? So why there was a need for multi-core? The Intel processors, which came into our, let's say, personal computers, they were not multi-core initially. So Intel, if you look back history, Intel, Celeron, then Pentium 1, 2, 3, so they were all single core. They were running at 4 gigahertz. They could perform very well, provide the kind of let's say application requirement you need. They could provide them. But then suddenly in the early 2000s, every processor started becoming multi-core. Now mobile phones are also multi-core. There is no single core. It is hard to find a single core processor. This is primarily because of the technological constraint. So the technological constraint in the 2000 or let's say late 90s, very clearly showed that a single core processor performance cannot scale because to scale performance, you need to run the processor at a higher clock speed, and higher clock speed means it will dissipate more power. Now, as it dissipates more power, you need special cooling mechanism. So your laptops have a forced air cooling mechanism. If you have a gaming laptop, you will have a liquid cooling mechanism. So that liquid cooling mechanism is much more expensive, right? So, but we want more performance. We can't use the laptop which was designed in 2000 and to live with that same performance, right? We need more performance, but we can't clock it faster because of the heat dissipation issue. So what was the basically this was the technological constraint. Application requirement wanted more and more faster processor. So architecture provided solutions. It said that okay, you can't run a single core at a very high speed. How about you split and have more number of cores and run them at a reasonable speed? And that's why you see that your multi-core processor, none of them operate more than maybe 2 GHz, right? Whereas in 2026 years back, Intel processors were running at 4 GHz. So why that speed has not been? Because of the power dissipation requirements. Okay. So basically, I will talk about this architecture in rest maybe 35 minutes or so, and I'll highlight one microarchitecture. Now, what is so? Okay, by name you can look at these abstraction layers. So I'll not go into the details. But what is this abstraction layer? So this abstraction layer, instruction set architecture, it is a contract between software designer and the hardware designer. It's basically a theoretical definition of how the hardware will behave, and who is given this theoretical definition. This theoretical definition is given to the software program. That okay, you can assume that this is the hardware, how it will behave. Now I am emphasizing the fact that it's a theoretical definition. It may be very far from what actually the hardware is. Okay. Now this contract, if you basically honor that contract while you write your code and while you design your hardware, then the software will work on the design hardware. Because if you are not following any instructions that happen and come up with a processor, then who will use that processor? Who will program that? That's why while we say that we want to become a semiconductor design hub, we have to be aware that to become that semiconductor design hub, what all we should be aware of? We should be aware of the instruction set architecture, and whatever hardware we design, we should be following, or we should make sure that our hardware follows some of the ISAs or instruction set architecture. Otherwise, the programmer will not be able to program. If I design something very unique, I have to only program, and that is not a scalable solution. Okay. So what are the very popular instruction set architecture? Intel, AMD, they uses an instruction set architecture called x86. It was proposed by Intel and then taken forward by AMD and Intel together. It is a very popular instruction set architecture. Then in your mobile, the instruction set architecture which is there is by ARM. Okay, so all your Snapdragon processors are using ARM. Even Apple uses ARM. Now, all these are proprietary instruction set architecture. So basically, if you want to design something, you sometime or other you have to either go to ARM or x86, basically Intel, to get this thing running. Now, from University of Berkeley, there is a open source ISA called RISC-V, which is an open source ISA, and it has become quite popular, and it's day by day it's becoming more and more popular. It's open source, so you don't have to go anywhere to design your hardware or software using this ISA. And the government of India, as well as many other governments, are focusing a lot on this ISA so that the future products can be built using this 5 ISA. Now, if we want to design something using RISC-V ISA, we have to know what this RISC-V ISA is, and it's a very popular ISA, as I mentioned, and of designs are coming up using this RISC-V. So I will quickly try to. I need to switch to another file.
This one, right?
Module 4. Okay. So I'm also. So basically, we can quickly go to RISC-V ISA and see. So typically, for designing this kind of a processor using RISC-V ISA, there are two main. One is called data bus design, and then the control. So we'll be focusing primarily on the data bus. I'll not have time to go through this, but typically, to know the performance of a, let's say you design a processor, somebody else designs some other processor, how do you know which one is better? So there was no quantitative approach to evaluate different processors for quite some time. Then there are two famous authors, again from Berkeley, Hennessy and Peterson. Their books are quite popular in computer architecture. So the book title is A Quantitative Approach Towards Computer Architecture. And they propose that, okay, there should be some quantitative measure to basically evaluate processor. And the evaluation metric they gave is basically if I run a same code in both the processors, what will be the execution time? And the execution time depends on how many instructions you have in that code. And now, basically, how many cycles each instruction take to execute. And finally, what is the cycle time in seconds? So I can have my hardware which has a cycle time of let's say 1 second. Somebody else might design a hardware where the cycle time is let's say 1 millisecond. So based on that, I can figure out what is the execution time of that processor. And while we design this processor, we have to keep in mind the cost, power, performance, etc. Now, why I was emphasizing the fact that this is a theoretical definition. These ISAs are theoretical definitions or contracts to the software, because you can see that you will have different configurations of smartphones as well as laptops in the market in different price brackets, but all of them will be running the same operating system or can handle the same application. For example, you can run Word application in a IC processor based laptop, which will cost you maybe 40,000, or an i9 processor based laptop, which will cost you 2 lakhs. Same Word application will run because the theoretical definition of the hardware, both cases are same. But now, what is the difference? The way the hardware has been designed. One case, hardware will give you lot more performance, but for that you have to pay more cost. it will possibly consume more power, and so on. So let's look at the now this processor has a lot of instructions, not a lot, but still there are different types of instructions. So some instructions are called R-type instructions. So R-type instructions are instructions where, remember that we are talking about now at a lower hardware level. So you have to give arithmetic and logic unit instructions like add, subtract, logical operations like AND or etc. This is set less than. Now, in R-type instruction, all the operands. So operands are basically the values on which I want to work on. For example, I want to add two numbers. So the two numbers are my operands. So in case of R-type instructions, both the source operand as well as the destination, the results which will be stored, the results which will be coming out, all of them are stored in some register. Now, okay, just to familiarize ourselves, what I am talking about, a typical computer is nothing but this. So you have we call it CPU, central processing unit. It has an ALU or arithmetic logic unit, and there I have, let's say here I have memory, and there is something called program counter. Okay, so program counter is kind of a register which can hold a particular value, which is an address value. So all our processors follow this kind of a block diagram. So your instruction and data is stored in memory. So whatever you want to do, all your instruction and data will be stored in memory, and this is your CPU. It has, of course, basically CPU has some control unit and arithmetic and logic unit and something called a program counter. Now, when you switch on this, so this is your computer. So when you switch on, the program counter has an address, and it tells that, okay, this is the address where you need to go in the memory, fetch that particular instruction. So, and then there is a mechanism to update this address. So every time you switch on your computer, this is the program counter value, which is basically fetched from memory. Now, after getting this content of this particular memory, the CPU actually processes that instruction. So basically, it goes to that memory location, fetches the value, and now CPU interprets it. That is the first instruction CPU has to execute. Now, after interpretation, if it is an arithmetic operation, it will ask the ALU to do certain things, and the result will be again stored back into the memory. And then there is a mechanism to update program counter. So the next instruction it fetches and keeps on doing this. So that's what your computer is. And this model of computer is called stored program model. Now, because the way it is, and this model has been from the first computer which one woman designed in early 1940s. Since then, we are calling the same compute model, stored program computer. Now, when we talk about AI algorithms, etc., one of the challenges is becoming that need lot of data. So when you have lot of data stored in this memory, and every time you want to work on that data, you have to get that data here. So there is a basically, and your processor can do lot more things, but it doesn't have the data because the accessing this memory is a slow process. And that's what is called von Neumann bottleneck or processor memory bottleneck. Now, to address this, basically people are talking about, can we design our computers which will act more like our brain? Our brain doesn't work like this. Our brain doesn't store instruction and data in memory somewhere else. Our brain works using neurons. So these neurons are very highly connected network, and based on our experiences, these different neuron paths get more and more basically stronger. So there are now discussions and there are research going on that, okay, can we move from this stored program model to neuromorphic computing, neuron-like computing? Some people are talking about, oh, I have my data in this memory. So can I do the processing here itself? So it's called in-memory computing. In-memory computing or near-memory computing. So you will find both the terms. So memory is designed to store data, but you are saying that, okay, I can build a logic here in the memory itself. And let's say if I need to do some logical operation on the bits, I will do it in the memory itself. I will not bring the data into the system. But assuming that, so these are all research areas where people are working. But the processor we are looking at, or all the processor we are using today, follows this. Memory, CPU, you need to get the data and instruction from memory. Now, of course, this is a very, as you need to read the data from memory, it's a slow process. So there was some compromise. It was saying that, okay, can I use some resistors inside the CPU where I put the very regularly used operands in the resistors? Now, in this RISC file, it also says that if you want to do some ALU operation, all your values should be in the resistors, and the result will be also stored in resistors. And if you want to store it in memory, so you have to use store instruction to store it back into memory. So that's where this R type instruction comes in. So basically all your operands are in register. You need to load the data from memory to these registers before you perform an operation. For example, I want to add 5 plus 7. Okay, and I want to store this result in a memory location, let's say. Okay, so what I have to do, I know that 5 is stored somewhere in memory, 7 is stored somewhere in memory. I will load 5 to a particular register, let's say R1. I will load 7 in another register, let's say R2. And then I will write add. Let's say the result will be stored in R3. So R3 is the destination register. R1 and R2 I will add and store it here. Okay. So this is an R type instruction. Now the result is in R3. I want to store it in this memory address. So what I'll do, I'll write a store instruction saying that store the value of R3 into the memory location A. So that's how I will store the result back into the memory. There are basically memory instructions like load store. So LW stands for load word. So the quantum of data you want to work with is called word, and that's what is mentioned here. Similarly, there are branch instructions like branch is equal, branch is not equal, etc. Now, before we look into the microarchitecture of a processor, there is something called architectural state. Now, when we put a computer on sleep, let's say in the hibernate mode, when we switch it back, it resumes from where it was. So how it does that? It does this by saving the architectural states. Now, what are the architectural states? In a processor, the architectural states are the registers, the program counter, and the content of memory. Now, if you can save this architectural states before you hibernate or put it on sleep mode, you can resume where you were. Okay. So we'll start with this architectural states for designing our micro. As I said, like this is our processor. Now the architectural states are register file, and we have divided this memory into instruction memory and data memory. So there are two parts. Basically, logically, there are two parts. They can be physically the same memory. So I'll store instruction here, data here. I have the register file and the program counter. So these are my architectural states. Now I want to design my microarchitecture, this file microarchitecture around these architectural states. Okay, and we'll start with data path, and we will. Okay, so let me jump onto the microarchitecture design. So let's say this is the instruction location. In the instruction memory, this is the location where there is an instruction stored, and the instruction stored is a load instruction. So basically, we will put this address in our program counter. If I put this address in the program counter will fetch this instruction. So this is the instruction that will be fetched from instruction memory, and this is what it is showing, that after fetching this instruction, I have the instruction which is nothing but the load operation. Now for load instruction, essentially what we need to do, I don't know whether it's readable, but I will read it. So I want to load the register number 6, and what I want to load it with, I want to load it with the basically content of this address. The address is mentioned here. It's called base offset addressing mode. So the base of the address is stored in a register called X9, and the offset value is -4. So if I basically read the content of X9 and add -4 to it, I will get the address from where I have to get the data. And basically the -4 value is stored in the immediate format, and these are the fields which are denoted here. So let's go forward. So I have this instruction. I give this instruction to register file. Now from this register, basically this instruction, I know I have to read X6. Okay, no, I don't have to read X6. I have to read X9 because I will be updating X6. So I will give this address of X9 to my register file. So register file has an input address which I am giving X9. I will read the content of this register, which is, for example, let's say hexadecimal number 2004. So I got this number. I have the value -4. So the value -4 is extended to a 32-bit number by sign extension. So I get this 32-bit number. Now these two numbers need to be added. I will use the ALU. So I use the ALU to add these two numbers. I get the address. Now this address is sent to the data memory. After I send this address to the data memory, I will get the result as an output, which is the content of this memory location. This address or this data I need to write into my register file. Which register? X6. So I will now say that, okay, this is the data, and in X6 you should update this data. So that's how the load operation will be performed. So you see that our microarchitecture has the connections now to perform the load operation. So similarly, we can basically see how we can basically modify this circuitry here to update our program counter, because program counter has to give us the next instruction so that we can perform the next instruction. So let's say we move to another instruction, like store instruction. So in the next instruction location, we had this instruction, which is a stored instruction. We can read it. In the stored instruction, we want to store the content of this register in this memory location. So I have to read the content of X6 because this is what we need to be storing. So X6 comes out. This is the data which needs to be written in the data memory. X9 is the base address, so I will read X9, add the number 8 to it, and this is the address I will get. So I give this address and the data to the memory location so that the data can be written or stored in the memory. So this is the store operation. So let me move to basically a OR. So the logical operation OR, I want to perform OR on X5 and X6, the content of X5 and X6, and the result will be stored in X4. So what do? I decode this instruction. I give that, okay, read X5 and X6. So you read X5, give the address of X5 and X6. You read the value. So let's assume that the values are 6 and 10. And now you will be performing the OR operation. After performing the OR operation, you have the result. Now this result need to be written in X4. So you will be passing this result as a result to this register file, and you will be giving the address that okay, X4 is the location where this value needs to be updated. So you can basically whatever we are doing now, just wearing this architectural stage and putting some markers and the ALU, you can design your micro. Now, why it is important or why it is interesting? Let's say I want to design a smartwatch. Okay, so let's say I want to design a smartwatch and I want to have some feature in that smartwatch which currently none of the smartwatches can do. For example, let's say I want to monitor attentiveness. Very happy, right? If I have a smartwatch and ask all of you to wear that smartwatch and I have the data, who were attentive during the talk, that will be very appropriate. So now how do I add a feature like let's say detecting attentiveness? Now I can say that okay, you have your traditional ALU here, which can perform this arithmetic logic operations, etc. But for the attentiveness detection, I need a special function. I need to do some, let's say, whatever data I'm collecting. Let's say I'm collecting your pulse plethysmograph data, which typically what the smartwatches collect to measure your heart rate. I want to collect that data. I want to run a fast Fourier transform on it. Now, if I want to do fast Fourier transform using this ALU, it will feel battery like anything, right? So I want to do some modification in the microarchitecture so that it can perform fast Fourier transform efficiently. What I can do, I can add an additional module, which I will call it as a hardware accelerator. As soon as in the instruction decoding stage, I realize that, oh, the basically user wants to perform this fast Fourier transform on the data series, then instead of using this data path, I will be routing the instruction to my accelerator. And I'll ask the accelerator to efficiently perform this fast Fourier transform. Current smartwatches or current processor. So if you think that okay, I can take a RISC-V based processor from the market and design this, you will not be able to. You have to do the modification yourself to have that additional accelerator in your design. So that's why we need to know. We need to know what are the bottlenecks. For example, many times the bottleneck is you are reading a time series, lot longer data. Let's say you have a 10,000 data points will come from your smartwatch, which you need to work on. Now, if you use the same stored program model, where let's say you will take a chunk of 32 bits at a time out of this 10,000 data, you will spend a lot of energy in let's say fetching the data, working on it, and repeating this operation. Maybe intermediate results also you need to store and so on. Instead of doing that, can you keep the 10,000 point long data as a vector and bring that vector and perform vector operation on the microarray? So that means I want to have a vector extension to this RISC-V. And I want basically vector extension, I can work on vectors. For example, I want to find out the peak value in this long 10,000 long vector. So I can perform these operations using the vector processor. So these are the modifications you can do if you understand the existing microarchitecture and you can build on top of it. So there are a lot more things. Basically, I have skimmed through. My objective was to give you a sense that the processor, if we want to understand it from the fundamental understanding. So if any processor I can model it like this, so doesn't matter how complicated the processor is, whether it's a supercomputer or it's a mobile phone processor, every processor follows this structure. So I have to find out the CPU, the registers, and the memory. This is what is all processors will have. And I have to understand their interconnections, how they are basically performing the different tasks it is supposed to do. And then we can basically identify bottlenecks and we can improve on that. We can redesign, we can come up with newer designs, etc. So in our team, we are working on several of this kind of projects. So where we want to use RISC-V for edge computing, whether it could be smart camera, it could be for drone applications. So basically indigenous drone with capabilities which, let's say, state-of-the-art drones don't have. So if you want to design something like that, or let's say you want to add security features in that. One of our recent work is, let's say we use this processor in a drone. Now, in let's say in war kind of situation, there will be thousands of drones flying around. Now, how do you identify which one is basically your own and which one is enemy's drone? And there will be enemy drones which will be posing like your drone. So you have to identify and detect. So this becomes like a very, very critical thing, and you have to do it in a split of a second. And the way you do this identification, it should be secure enough so that the enemy can't mimic it. Because if enemy can mimic it, then you will not be able to distinguish your drone and the enemy drone. So one of the tasks which we have done is basically we have looked at the ALU and we have tried to find out some signature which are very unique. These are called physically unclonable functions. You can clone the whole design, but you can't clone the signature. So basically these are called intrinsic physically unclonable functions we have implemented in the ALU, and using that we can generate some unique fingerprint of the drone which can be used for detecting it or which can be used for identifying it among all the drones. We have also so hardware security is one thing which we are focusing very aggressively. Apart from that, we are looking at performance, as I mentioned, like edge computing. So let's say your drone can see a large area, and now you want the drone itself to detect whether there is any movement or not. Now, to detect movement, it can run all the standard AI algorithms, but then if you run it on your drone platform itself, you need to put a lot of resources, which may be expensive and infeasible to have. So basically, can you have a cloned version of it? So that's where we are basically exploring edge computing for drone and other applications. So Basically, there are many other things which we are working on. If I can go back to the previous file. अरे ये open ही होगा ना? हाँ हाँ मत करिए स्लाइड नीचे करना है और नीचे हाँ हाँ ये वाला स्लाइड
ये वाला
हाँ
ये वाला ना
हाँ हाँ
फोटो
So we are working on these different topics in our lab called Advanced Quantum Systems Lab. Some of the research areas are mentioned here. If you can read it. And we have a big group of PhD students, master students, and undergraduate researchers in our group. So this, okay, not visible. And we have a lot of industry as well as academia collaborators. So I'll stop here. My email etc. mentioned here. It's not visible, so but you can get it from faculty members. Thanks for your attention. I'll stop here and if you have a
comparedness to increase cost.
Thank you, sir, for your insightful talk. Your session has truly enriched our understanding of future semiconductor technologies and modern computing systems, and inspired us to think beyond the classroom. We are truly grateful, sir, for your time, efforts, and sharing your valuable expertise with us today. I now request Dr. Neha Goyal ma'am to present the memento and certificate to Dr. Subraj. Okay, thank you, everyone. Now we have a group photograph.